All right, let's go ahead and get started. I want to welcome you back to Unit 15. This is acid-base equilibrium and buffers. Folks, last time we were looking at a situation in which we had a strong acid and a strong base, and we saw that it was very straightforward to calculate the hydrogen ion concentration, or the pH, because of the fact that there was complete dissociation of either the strong acid or the strong base. What we want to take a look at now is we want to look at a weak acid or a weak base situation. In number 9, we'll look at a weak acid. It says calculate the magnitude of the equilibrium constant for benzoic acid, that's HC7H5O2, if a 0.1 molar solution has a pH of 2.590. Okay? So here we go. How do we do this? Well, we know this is a weak acid because, well, it's not one of the strong acids, right? We memorized the 6 strong acids, and benzoic acid is not one of them. So it's a weak acid. And anytime we want to know something like an equilibrium constant or a hydrogen ion concentration or a pH or whatever, we're going to need a Rice table. So I've set one up here. We've got HC7H5O2. That's the benzoic acid. We're always going to mix it with water. We're always going to place it into water. But water is a liquid, so we'll just put an X here. So there's no beginning and ending equilibrium concentrations for these. So just put a big X and we'll ignore this, but you do need to put that H2O in there. And we use a double arrow because of the fact that, well, it's an equilibrium, right? So what's happening here? What's happening is that we're losing a proton. So in this process going from here to here, this is the acid, this is the conjugate base, right? And so we have plus H3O plus, right? Or hydronium ion. So it tells us in the problem that we've started with a 0.1 molar solution. So, and the equilibrium always goes to the right, right? We always start with something on the left-hand side and go right with acids. That makes it a lot easier than what we were doing in the equilibrium unit. So 0.100 is what we start with. We start with nothing of the benzoate ion and nothing of the hydronium ion. So 0 and 0 for these. So we're going to lose from the benzoic acid and gain here. How much? I don't know. So we're going to say we're going to lose X. So minus X here, plus X here, plus X here, right? So now let's add up. In the equilibrium expression, we're going to have 0.100 minus X. We're going to have X for the equilibrium concentration of the benzoate ion and X for the H3O plus concentration, right? At equilibrium. Now, if I want to write an expression, what I'm going to do is I'm going to put the products over the reactants at equilibrium. So benzoate ion, that's C7H5O2 minus times H3O plus concentration, those two multiplied together divided by benzoic acid is going to be the expression. Not the number, but the expression, okay? All right, now what I'm going to need to know is I'm going to need to know what to put in here. So what information am I given? I'm given the pH, okay? I'm given a pH of 2.590. From that, I'm going to be able to determine the hydrogen ion concentration from this expression. pH, which is 2.950, so that's 3 significant digits, by the way, 5, 9, and 0, is equal to minus the log of the hydrogen ion concentration. So I'll exponentiate both sides to get the hydrogen ion concentration. You do that on your calculator. I want you to check to make sure you get what I get. So the hydrogen ion concentration, it turns out, is this number. At equilibrium, it's 0.00257, right? Again, notice I'm going to need 3 significant digits, so 0.00257 for the hydrogen ion concentration. So now I know this value, I know this value, and I know this value, okay? So what I can do then is I can start plugging things in. So if I know the hydrogen ion concentration is 0.00257, that's this value and this value, I can just say 0.00257 squared divided by 0.1 minus that value is this number. You check it again, by the way. Don't just take my word for it. 0.00974. And so when I plug that in the calculator, again, square on top, divide by what's on bottom, here's what I get. 6.78 times 10 to the negative 5. Now, should it surprise you that the Ka is so small? And the answer is absolutely not. This is a weak acid, right? So that means that in the equilibrium, that the equilibrium lies further to the left than it does to the right, right? It's not equal going backwards and forwards. It's further to the left than to the right. So I expect to see a small number, and that's indeed what I get. I get a small number for that Ka, all right? Hope that makes sense. Let's move on to the next one. All right, in this one we want to take a look at a weak base. So we looked at a weak acid in the last one. We're going to try a weak base this time. It's going to be very, very similar. It says calculate the magnitude of the equilibrium constant for an aqueous solution of ammonia. So we know ammonia is a weak base, right? So if a 0.1 molar solution has a pH of 11.130, okay? So first thing we're going to do is we're going to set up our rice table, right? So in the rice table, what we see is we're going to have our base plus water. Remember, always put in water in equilibrium with, well, if this is the base, this is the conjugate acid, the NH4 plus. The NH3 gives or receives a proton, I should say, from the water. So it's going to become NH4 plus and OH minus, right? So now that we've got the reaction, let's do the initial. So we're told we've got initial concentration of 0.100 molar. For that one, remember, cross out the water. We don't use that because it's liquid. It's not aqueous. We always start out with nothing for the product. So that's going to help us a lot because we don't have to worry about whether it goes forward or backwards. It's always going to go forward direction. Also, the other thing, we don't have to worry about coefficients because we're always trading a single proton, right? So we don't have to worry about 2s and 3s as coefficients and superscripts. So that's another thing that makes this easier really than regular equilibrium problems. We're going to lose on the left-hand side and we're going to gain on the right-hand side. So minus x, plus x, just like that. So now what we're going to do is we're going to fill out our equilibrium line. So we've got 0.10 minus x on this side, 0 plus x, 0 plus x, and now we've got our equilibrium line all set up, right? Now, they tell me that the pH is 11.130, right? But this is a base problem. We're working with a weak base. So the first thing we're going to need to do is we're going to need to convert that pH to a pOH. It's easy. What we're going to do is we're going to say 14 minus the 11.130 that they give me, and I get 2.870 to the correct number of significant digits, okay? Right? I have a pH of 2.870. So now what I'm going to do is this. Remember, only the numbers to the right of the decimal count. So now what I'm going to do is this. I'm going to exponentiate. And when I do that, I get 10 to that little caret there means exponentiate, negative 2.870. Do this on your calculator. Here's what I get. I get x is equal to 0.00135, okay? So that is our hydroxide ion concentration, right? That's our hydroxide ion concentration. So I can plug that number in there, I can plug it in there, and I can plug it in right there, okay? So that's going to allow me to fill in my Kb expression. Now remember, the Kb expression is the products over reactants, so that's going to be NH4 plus times OH minus over the reactants, which is NH3, right? So NH4 plus OH minus over NH3. And we've just determined that the OH minus concentration and the NH4 plus concentration for that matter is 0.00135. So we'll say 0.00135 squared. Then if we say, remember in the NH3 column, we had 0.10 minus x, really that should be 0.100 minus x, we get this number. So you do the calculation, this is what I got, 0.0897. So when you square on top and divide by Kb, the 0.0987, you get Kb. And we get 1.85 times 10 to the minus 5. Again, it should not surprise us that this is a small number, right? Because it is a weak base, right? So it shouldn't surprise us that it's that small. Okay. So let's take a look at this last one. Number 11 says calculate the pH of a solution which is 0.712 molar CH3NH2. It's called methylamine. So when you see that nitrogen, that's your signal that that's an amine, right? So we call this methylamine, and it has a Kb value. They're telling me a 4.4 times 10 to the minus 4. So how do I know that this is a weak base? Well, first of all, anytime you have an amine, that's going to be a weak base, okay? And secondly, they're giving me a Kb, right? So that's my signal that this is a weak base situation. So let's write the Rice table for this situation then. And here's what we've got. We've got CH3NH2, that's the methylamine, plus H2O. Don't forget to put that in every time. In equilibrium with the ion. Remember, if it's a base, it's going to, is it a proton acceptor or a proton donor? Right? It's a proton acceptor, right? So it's going to take a hydrogen from that water just like that. And so on this side, it's going to be a CH3NH3 plus. Just tag that hydrogen onto the end and make it CH3NH3 plus OH minus, right? So we got hydroxide at the end. So remember, we're starting with a 0.712 molar solution of the methylamine. We always start with something on the left and nothing on the right in the initial row, right? So we have 0 and 0 here. We're always going to shift right. We're always going to move to the right-hand side. Even though the equilibrium is going to be to the left, right, and overall to the left, we're going to start with something on the left and move to the right. Not very much because it is a weak base, but we are going to be moving to the right. So that means we're going to lose some of this 0.712. So in the change row, we're going to say minus x. I don't know how much I'm going to lose, so I just say minus x. Over here, I'm going to gain some. Don't know how much. So in math, just like in math, where you say, I don't know what it is, you call it x. So plus x over here. Now, let's talk about this equilibrium row, because this is important here. Theoretically, this should be 0.712 minus x, just like that, right? Why? Because we lost some of that, right? And, of course, this would be x. 0 plus x is x, and this is x. But here's a little trick that I want to show you that you can use with weak acids and bases on the AP exam. You can't do that in here, but you can do it on the AP exam. Let's write an expression for Kb first of all. I'll show you how this is going to come into play. Kb is equal to the products over reactants. So the products of CH3NH3 plus OH minus, that's that product, over the CH3NH2, right? So the Kb we were told in the problem was 4.4 times 10 to the minus 4. And that's equal to, both of these are x, so we're just going to say x squared. But look what I did here. I didn't say 0.712 minus x. I just said 7.12. Why did I do that? Why did I ignore that x? Well, here's why. Because on the AP exam, that x is going to almost certainly, and I would almost say with absolute certainty, that x is going to be what we call negligible. Let me write that. Negligible. I think that's the correct spelling. I hope so. It's negligible. The reason is because of the fact that some people have nicer calculators than others, and they can do quadratic equations, and quadratic equations would be what we would need. A quadratic would be what we would need in order to do this. If this was a 0.712 minus x, you'd have a quadratic, right? You'd have an x squared, and you'd have an x, and you have a constant. But what we can do is, on the AP exam, you can't do that in here. You're going to have to do the quadratic in here. But on the AP exam, you can just ignore that x, and I'll show you how you can prove that it was okay to do that in just a moment. We're going to solve for x. Pull the 0.712 up, solve for x, which is the OH minus concentration. You do the calculation there. 0.018 is what I get. So now I know the OH minus concentration. It's easy enough then, using POH is equal to minus the log of the OH concentration, to determine the POH. Again, you do it. I got 1.74 to the correct number of significant digits. 2 significant digits here, I need 2 there, and that's what I put. So 1.74, so the pH then is equal to 14 minus that, 12.26. So that's my answer. Here's what I'm going to do. I'm going to use the 5% rule. What I started with, okay, I'm sorry, the change over the original times 100. If That comes out to less than 5%.